Hello! In the last tutorial, we built a Concord model that generates a musical phrase based on some random variables. Before moving on to using machine learning to generate variations on existing melodies using such a model, we will first use factors to alter the distribution of the random variables that this model is built on. To do this, we will first separate the factors that we are about to add to the model from the outputs that we have already created. This step is optional but highly recommended since it increases modularity and just makes models much more legible for other designers and also for yourself. First, we will add our new model. So simply right-click in the content browser, add a Concord model and name this phrase factors. Then we will grab the boxes from our original model, cut them with Ctrl X and then paste them into the new model with Ctrl V. In place of the old boxes, we will now add some parameters. So type parameter int when dragging off of this repeat node where the progression was and name this progression. We will also set the default shape on this parameter so that the model knows what to expect. And this was 8 just as the box. We will do the same for the melody down here, which was a box. We will turn it into a parameter, name this melody, and set the default shape to the one it was before, and that was 8 by 4. Now that this is set up, we can move back to the phrase factors model that we've just added and add the phrase model that we've created earlier as a composite. And we'll just call this phrase. You can think of this composite as a node that basically contains this entire graph, and it exposes the parameters and the outputs as pins. The key and the progression pin we will not use, so we can set them to local in the original model, just by hitting this interface local checkbox down here. And I'll do the same thing for scale. Switching back, we now only have the progression and the melody pins, which we can connect from our boxes, and the outputs, which we just want to pass on. To do this, we can simply right-click anywhere and type to output, and it will generate the outputs from the selected output pins. Now we can test if this model works. First, we have to set the preview sound once again for this model as well. So the model does the same as it did earlier, but now we have some modularity and we can work on applying factors to these random variables in a bit of a nicer environment with less clutter. So what do I mean by saying applying factors? Basically, these random variables right now follow a uniform distribution, but we can utter our preferences. We can tell the model which configurations are more likely by adding factors to the model with scores. A high score means that the configuration that achieved the score is likely, a low score, the opposite. To illustrate this, let's first make a factor that tells the progression box that when we make a step from 1 degree to the next, we don't want a large step. We want a small step, like from 1 to 3, but not from 1 to 12. To do this, I will grab the all pin, create a range node, and I'll also duplicate this since we will need another one. Then on the first range node, I'll have it go from 0 to -2, and on the second range node, I'll have it go from 1 to -1. So if the last one is at -1, it goes all the way to the end. Then I will also connect all to this range node. And now by adding a subtract node and connecting the output pins from the range nodes to the input pins on the subtract, I have created a chain of differences, where each value here of each difference here is the difference between two consecutive random variables in this box. Then I'll take the absolute value of that, multiply it by some value, let's say -2, and then pipe this into a factor. A factor is a node with a single score input, and this score is used to compute the probability distribution for the box. I'll grab these nodes that I've just created and I'll tidy them up a little bit by straightening the connections and moving them a bit out of the way. Now if I press the spacebar again, we can see that the progression box generates progressions that don't have large steps in between them. Also, as you may have noticed, the colors have changed. So if I run the model and I don't have any factors set up for a box, so it's a uniform distribution, this distribution has maximum entropy, meaning it is as random as possible. This is displayed by using red colors next to the pins. Red as in hot, it changes a lot. a distribution that has low entropy, which is quite centered around certain values that appear very frequently, will have low entropy, and thus it's blue, so cold, it doesn't change a lot. There are two ways we can display these entropies, and under live feedback in the details you can change between them. Conditional simply considers a random variable and all of the other observed values and then computes the entropy, whereas marginal considers the random variable and all the other states that the other variables can take. So it sums over all possible configurations. And as we can see, having set up this chain doesn't actually affect the marginal distribution, since it depends on where we start, and where we start is completely random. Thus, the marginal distribution is still completely uniform for each random variable individually, but the conditional distribution here is very much not uniform, and we can use a viewer node to actually display the node by hitting spacebar again, and we can see we only have bars at 11 and 12, because these are the predecessor and the successor of this random variable, and the others are very unlikely to happen because of our -2. I will settle on -1.5 or 1.2 for the minute. And let's move on and create another factor. If I press the spacebar a lot, I can see what I can expect from my progression box, and in general, I want to have these high values for the progression degrees to be rather unlikely. To do this, I can simply once again drag off the all pin and use a multiply node to simply multiply the value of the random variables by -0.05, and then we pipe this into a factor once again. Now, if I press spacebar a lot, we can see it is less likely to go into the double digits. And if I increase this by a bit, it'll be entirely unlikely. And we can display this using the marginal distributions on here. We see this kind of downward slope towards the higher values. Now that we have set up our progression box, let's move on to the melody box and add some factors to this. Here I have some ideas. First, I want the melody and the progression to be kind of dependent on each other, and thus we need to combine these values somehow. To do this, we can simply subtract the progression values from the melody values, or rather the other way around. This works because the shapes are compatible. The progression box is of shape 8, whereas the melody box is of shape 8x4. Concord uses a technique called broadcasting so that operations on multidimensional arrays which are compatible can be performed in an intuitive way. In this case, each one of the progression values is broadcasted to 4 values in the melody box, because up to the value of 4, the shapes are identical, and afterwards there's only one progression value for every 4 melody values. So this subtraction will give us 8x4 values, which we can once again take the absolute value of, and then we will actually use a modulo node to wrap this around 7, because we don't actually care about which octave this degree difference is in. And having now this degree difference, we want to have some differences be more likely than others. To specify which are more likely, I'll use a parameter, an integer parameter, call that preferred degree or preferred degree differences, and we'll use two values, 0 or 4, right? So 0 would be within an octave and 4 would be within 4 degrees. So the difference of 4 degrees is like from 1 to 5, right? From the 1st to the 5th, which is a very harmonic interval. Now I want to kind of combine my values here with my value right here. But this one is of shape 8x4, and here we now have shape 2. So I will use the default shape on the parameter to set this to 1x1x2. And now once again the shapes are compatible, since we have in the first 2 dimensions 1, and these can then be broadcasted to this 8x4. And then we'll have 2 values for each of my preferred degree differences. Now I can simply check for equality between the computed differences and the preferred differences. Then I will use an any node, and I will use this any node in the last dimension, which we can enter by putting -1 into the dimension index box right here. This will get rid of the 2 dimensions that this preferred degree differences node has introduced, and we don't care which one it is equal to, so this is why we put an any note right here. And then we can use this, the usual pattern, just multiply a boolean, which is either 0 or 1, by some value that we want to use for a score. Let's call it 5, and then pipe this into a factor. And as we can see here, when we have a degree of 1, now the melody comes up with a degree of 12, or 1, or 8. And all of these are either octaves or fifths for this degree of 1. Right now, we have made a little mistake. We are not accounting for zeros in the melody box with this factor. A 0 in the melody box, we have assigned a special no-op meaning to this. To account for this and make no-ops also likely and don't compute degree differences with these no-ops, we can use a condition node. So I'll just move this down a little bit, add my if. As a condition, I will simply use the values of the box, since for 0 this will be false, and for everything non-zero this will use the true value. And then we will hook up the output of this multiplier with the true value when a node is present. But when no node is present, we will use the false value, where we'll assign the same score as here. And so that we don't have to enter the same value twice when we change this, I will use a parameter of type float, call this preferred degree score, and set it to 5. And then we'll also connect this here to the false node, so a no-op has the same score as a preferred degree, and then we'll connect this up to the factor. And now we get some more zeros in here, meaning we get some longer notes as well. I want to add one last factor to this model to add a bit of rhythmic structure to the melody. To do this, I will first add a parameter of integer type and call it mask. We will use this mask as a kind of rhythmic mask, so we'll add 8 values to the default values array, and then we can use zeros and ones to specify on which 16th notes I want a note to happen and on which I want a no-op to happen. We will then repeat these 8 16th notes across the 32 16th notes that constitute our melody. So first off, I will just create a very simple rhythmic pattern where we have 8th notes, but on the last 2 we have 16th notes. And now we want to broadcast this across our melody box. Our melody box is of shape 8 by 4 and our mask is of shape 8. So in principle, these are compatible. However, it would be a bad idea to just add some binary operations on these two right now, because we want these mask elements to be consecutive. And right now we have 4 elements for every 8, so it would not be consecutive here. To change this, we can use a reshape node. So once again, we'll drag off the all pin of the melody box and add a reshape node. And here we will now have this be 4 by 8. Now the last dimension is 8, so we can repeat an 8 element sized array across the last dimension, and it will always be consecutive. However, for the broadcast to work, we need to make the shapes compatible. Right now this is of shape 8, but we can change the default shape to be 1 by 8 of this parameter, and now the shapes are compatible, since we have a 1 which will be broadcast to this 4, and then 8 is identical. Next, we will draw off the reshape node and add a not equal node, which we will use to transform our melody into a sequence of zeros and ones, either a no-op or a node-on event. And then we will check for equality with our mask, and this will automatically broadcast to check for this 4 times across the melody. Now we can once again multiply this value, which is either 0 or 1, by some score, for example 5, which is quite high, and then pipe this into a factor. Now if we observe our melody box, we can see that wherever we have put a 0 in our mask, which is repeated 4 times across these 32 values, a 0 appears in the random variables, and it's very likely to be 0, which we can glean by the blue color right here. Where there is a 1 in the mask, we have still a choice of different notes. So let's take a listen. What we can see here is that even though it's quite sure it'll be 0, right here it has actually flipped to a 7, so it can still happen. Alright, now we have turned a uniformly random melody generator into one that has a bit of musical knowledge. In the next tutorial we will use machine learning to use data to come up with these factors instead of having to input them manually. Thank you, bye!